Wherever you are in the world, whatever time it is, I'm so glad you're here with me tonight. We're about to embark on a journey to one of the most mind-bending frontiers of theoretical physics, where the familiar laws of reality bend and twist into something almost unrecognizable. What if I told you that black holes, those cosmic monsters we've come to know and fear, might not be what we think they are at all? Tonight, we're diving deep into the mysterious world of Gravastars. Objects so strange, so counterintuitive, that they challenge everything we thought we knew about the most extreme environments in the universe. If you find comfort in these gentle explorations of cutting-edge science, I'd be grateful if you'd consider subscribing and hitting that like button. It helps the algorithm find more curious minds like yours, and it would mean the world to me as I work to bring you these cosmic mysteries. The visuals are here to guide you, but feel free to close your eyes, breathe deeply, and let your imagination drift through the cosmos alongside me. There's absolutely no pressure to stay awake through the entire journey. Sometimes the most profound insights come when we allow our minds to wander freely through these vast, theoretical landscapes. I'd love to know where you're listening from tonight. Drop your location and time in the comments below. Picture yourself standing at the edge of an infinite ocean on a moonless night. The water before you is perfectly black, so dark that you can't tell where the sea ends and the sky begins. Now imagine that somewhere in that darkness lies an object so dense, so gravitationally powerful, that not even light can escape its grasp. This is how we've long imagined black holes. Cosmic prison cells from which nothing, absolutely nothing, can ever return. But what if that image is incomplete? What if these mysterious objects aren't quite the inescapable dungeons we've imagined them to be? What if, instead of being tears in the fabric of space-time itself, there's something far stranger and more wonderful? Welcome to the world of Gravastars. The name itself sounds like something from science fiction, doesn't it? A portmanteau of gravitational and star, these hypothetical objects represent one of the most radical reimagining of extreme astrophysics in recent decades. They're not quite stars as we know them, and they're definitely not black holes. They exist in a theoretical realm where the very foundations of physics dance on the edge of what's possible. To understand what makes Gravastars so extraordinary, we need to first journey back to the birth of black hole theory itself. For over a century, these cosmic enigmas have captured our imagination and challenged our understanding of reality. When Carl Schwarzschild first solved Einstein's field equations in 1916, just months after Einstein published his theory of general relativity, he discovered something that would haunt physicists for generations to come. Schwarzschild found that if you compressed enough mass into a small enough space, you'd create a region of space-time so warped that it would form what we now call an event horizon. Cross this boundary, and you've entered a realm from which no information, no matter, no light can ever escape. It's a one-way ticket into the unknown, a cosmic point of no return that defies our everyday understanding of cause and effect. For decades, this seemed like the final word on the matter. Black holes were accepted as inevitable consequences of Einstein's equations, strange but mathematically sound objects that must exist wherever matter becomes sufficiently dense. We built our understanding of stellar evolution around them. We use them to explain the most energetic phenomena in the universe. We even detected their gravitational waves rippling across space-time itself. But here's where the story takes an unexpected turn. In the early years of this century, a small group of theoretical physicists began asking uncomfortable questions. What if our assumptions about black holes were missing something crucial? What if there were other solutions to Einstein's equations that we hadn't fully explored? The journey to Gravastars began with a simple but profound observation about the nature of spacetime itself. Einstein's general relativity tells us that matter and energy curve spacetime, and this curvature is what we experience as gravity. But the equations also allow for something far more exotic. They permit solutions where spacetime doesn't just curve, but where it can exhibit properties that seem almost magical. Enter Pavel Mazur and Emil Motola, two physicists whose 2004 paper would shake the foundations of black hole theory. They proposed something that sounded impossible at first glance. What if objects that appear to be black holes from the outside are actually hollow shells of exotic matter, surrounded by regions of space-time so strange that they make black holes look simple by comparison? These objects, which they christened Gravastars, would mimic black holes in almost every observable way. They would bend light around them with the same gravitational intensity. They would affect the orbits of nearby stars with identical precision. From a distance, they would be virtually indistinguishable from the black holes we thought we knew. But up close, the differences would be revolutionary. Imagine approaching what you believe to be a black hole. As you draw nearer, your instruments detect the familiar signs of extreme gravity. Space and time begin to stretch and warp around you. Light bends in impossible curves. Your clocks slow down relative to distant observers. Everything seems perfectly consistent with black hole theory. But then something extraordinary happens. Instead of crossing an event horizon and plunging into an unknowable singularity, you encounter something else entirely. A shell of matter so exotic, so unlike anything in our everyday experience, that it exists in a state of perpetual gravitational collapse that never quite completes itself. This shell, made of what physicists call dark energy or vacuum energy, exists in a delicate balance between the inward pull of its own gravity and an outward pressure that defies conventional physics. It's neither collapsing nor expanding, but suspended in a state of perfect equilibrium that could theoretically persist for billions of years. But the true strangeness of Gravastars lies not in their shells, but in their interiors. While a black hole's interior remains forever hidden behind its event horizon, a Gravastar's hollow core presents us with something even more mysterious. It's a region of space-time with negative pressure, where the very vacuum of space itself pushes outward with a force that balances the crushing weight of the shell above. This isn't empty space as we normally conceive it. It's a realm where the quantum properties of the vacuum itself become macroscopically important, where the subtle energy that fills even the emptiest regions of space suddenly becomes the dominant force shaping reality. It's as if the universe has turned itself inside out, creating a bubble of anti-gravity within a shell of conventional matter. The implications of such objects are staggering. If Gravastars exist, they would solve some of the most troubling paradoxes in modern physics. The information paradox that has puzzled physicists for decades simply disappears. because information falling into a gravastar doesn't vanish behind an event horizon. Instead, it becomes encoded in the structure of the shell itself, preserved for all time in a form that could theoretically be recovered. Similarly, the problem of singularities, those mathematical infinities that appear at the centers of black holes and make physicists deeply uncomfortable, vanishes entirely. Gravastars have no singularities, no points where the laws of physics break down completely. They're exotic, yes, but they remain within the bounds of mathematical respectability. But perhaps most intriguingly, gravastars offer us a window into the quantum nature of gravity itself. These objects exist at the intersection of general relativity and quantum mechanics, two theories that have resisted unification for nearly a century. In the exotic matter of a gravastar's shell, we might find clues about how these fundamental forces finally come together at the deepest level of reality. The formation of gravastars would be a process so extreme that it challenges our understanding of stellar evolution itself. When a massive star reaches the end of its life, it typically undergoes gravitational collapse that either creates a neutron star or, if the star is sufficiently massive, continues until it forms a black hole. But gravastar theory suggests there might be a third possibility, a narrow window where quantum effects in the vacuum itself halt the collapse just before a true event horizon can form. Picture the final moments of a dying star. The nuclear fuel that has sustained it for millions of years is finally exhausted. Without the outward pressure of fusion reactions to support it, the star begins its final collapse under its own gravity. Matter compresses to densities that dwarf even the cores of neutron stars. Space and time warp beyond recognition. In conventional theory, this collapse continues until it creates an event horizon and eventually a singularity. But gravastar formation requires something more subtle. At precisely the right moment, when the collapsing matter reaches a critical density, quantum effects in the vacuum itself must suddenly become important enough to halt the collapse. The dying star's outer layers form a shell of exotic matter, while its core transforms into a region of negative pressure spacetime. It's a process that exists on a knife's edge between different possible fates. Too little mass, and you get a neutron star. Too much, and the collapse continues to form a conventional black hole. But in that narrow range between these extremes, the universe might occasionally create something far stranger than either. The evidence for gravastars remains tantalizingly elusive, hidden in the subtle differences between these exotic objects and their black hole cousins. From our vantage point here on Earth, separated by vast distances from these cosmic mysteries, the distinctions are almost impossibly small. A gravastar and a black hole of equal mass would bend spacetime in nearly identical ways, their gravitational signatures so similar that even our most sophisticated instruments struggle to tell them apart. But nature has a way of revealing her secrets to those patient enough to look closely. The key lies in understanding how these objects interact with their surroundings, how they respond to the cosmic dance of matter and energy that plays out across the universe. While a black hole swallows everything that crosses its event horizon, never to return, a gravastar's shell creates a fundamentally different kind of boundary. Imagine watching matter spiral into one of these objects. In both cases, you'd see the familiar accretion disk, that blazing whirlpool of superheated gas and plasma that glows with the intensity of 1 billion suns. You'd witness the same gravitational redshift as light struggles to escape the intense gravitational field. The orbital mechanics of nearby stars would follow identical patterns, tracing ellipses and hyperbolas through warped space-time with mathematical precision. Yet there are whispers of difference, subtle signatures that might distinguish these exotic alternatives from their more familiar cousins. The way gravitational waves propagate from colliding gravastars could carry distinctive echoes, reverberations that speak of hollow interiors rather than singular points. The precise spectrum of radiation from their accretion disks might reveal the presence of a physical surface rather than an event horizon. These differences exist at the very limits of our current observational capabilities, requiring instruments of unprecedented sensitivity and theoretical models of extraordinary sophistication. It's like trying to distinguish between two nearly identical musical notes played by cosmic orchestras billions of light years away, where the slightest variation in tone might reveal entirely different underlying structures. The interior of a gravastar presents us with physics so exotic that it challenges our most basic intuitions about space and time. Within that hollow core, the vacuum itself becomes an active participant in the cosmic drama. The quantum fluctuations that normally exist as barely detectable whispers in empty space suddenly amplify into macroscopic forces capable of balancing the weight of collapsed stellar matter. This isn't the familiar emptiness we associate with the space between stars. It's a realm where the uncertainty principle operates on astronomical scales, where virtual particles become real through sheer gravitational intensity, where the very fabric of space-time exhibits properties that seem to belong more in the realm of science fiction than serious physics. The negative pressure that fills this interior space pushes outward with precisely the right force to maintain the delicate equilibrium that keeps the entire structure stable. Consider the profound implications of such a state of matter. In our everyday experience, we're accustomed to materials that either push inward under compression or push outward under tension. But the exotic matter that comprises a gravastar's shell exists in a state where it simultaneously experiences both conditions, creating a stable configuration that classical physics would consider impossible. This exotic matter isn't made of atoms or molecules as we know them. Instead, it consists of quantum fields in highly excited states, configurations of energy and momentum that exist at the intersection of particle physics and cosmology. It's matter that owes its existence to the deepest principles of quantum mechanics, where the distinction between particles and waves, between something and nothing, becomes beautifully blurred. The shell itself exists in a state of suspended animation, neither quite collapsing inward nor expanding outward. It maintains its structure through a delicate balance of forces that operates according to principles we're only beginning to understand. The gravitational attraction that tries to compress the shell inward meets the quantum pressure of the exotic matter that pushes outward, creating a stable equilibrium that could persist longer than the current age of the universe. But stability in this context is a relative term. These objects exist in what physicists call metastable states, configurations that appear stable on astronomical timescales, but might eventually decay into more familiar forms. A gravastar might maintain its exotic structure for billions of years, only to suddenly transition into a conventional black hole when some critical threshold is finally crossed. The transition process itself would be a spectacular cosmic event, releasing energies that dwarf even the most violent supernova explosions. As the exotic matter shell finally succumbs to gravitational collapse, the vacuum energy trapped in the interior would be released in a burst of radiation and gravitational waves that would be visible across vast distances. It would be the universe's way of announcing that another exotic object has surrendered to more conventional physics. Yet even these dramatic transitions might leave observable traces, signatures in the cosmic microwave background, or patterns in the distribution of matter that could reveal the past existence of these exotic objects. The universe keeps meticulous records of its most dramatic events, encoding them in the subtle variations of temperature and density that we can still observe today, billions of years after the fact. The mathematical framework that describes gravastars pushes general relativity to its absolute limits, exploring solutions to Einstein's equations that were never seriously considered during the theory's early development. These aren't simple modifications to existing physics, but rather explorations of possibilities that were always present in the mathematics, waiting patiently for someone bold enough to take them seriously. The equations reveal a universe far richer and stranger than we initially imagined, where the same mathematical principles that describe the gentle warping of space-time around our sun can also give rise to objects so exotic that they seem to belong to an entirely different reality. It's a reminder that mathematics often knows more about the universe than we do, containing within its abstract structures hints of phenomena that won't be discovered for decades or centuries. Working with these equations requires a delicate balance between mathematical rigor and physical intuition. The solutions that describe gravastars exist in a narrow parameter space where small changes in initial conditions can lead to dramatically different outcomes. It's like walking a tightrope suspended over an abyss of mathematical complexity, where every step must be carefully calculated to avoid falling into regions where the physics becomes either trivial or nonsensical. The quantum mechanical aspects of gravastar formation introduce additional layers of complexity that challenge our understanding of how large-scale structure emerges from microscopic physics. The transition from quantum to classical behavior, normally a straightforward process in everyday physics, becomes deeply mysterious when applied to objects massive enough to significantly warp space-time. These objects force us to confront fundamental questions about the nature of reality itself. What does it mean for something to exist in the quantum realm when that something has the mass of several suns? How do we reconcile the probabilistic nature of quantum mechanics with the deterministic predictions of general relativity when both theories become equally important in describing the same physical system? The answers to these questions remain tantalizingly out of reach, hidden in the mathematical depths of theories we haven't yet learned to fully understand. But the very existence of gravastars as theoretical possibilities reminds us that the universe is under no obligation to conform to our preconceptions about what should or shouldn't be possible. As we continue our journey through this cosmic mystery, we find ourselves standing at the threshold of even stranger possibilities. For if gravastars can exist, if the universe can create objects so exotic that they challenge our most basic assumptions about matter and energy, then what other surprises might be waiting for us in the vast darkness between the stars? Stars. The theoretical landscape of gravastars opens doorways to possibilities that stretch far beyond our current understanding of cosmic architecture. As we peer deeper into these mathematical mysteries, we encounter phenomena that seem to exist at the very boundary between science and imagination. Yet every equation tells us these objects might be as real as the stars we see twinkling in our night sky. Consider the profound implications of what we're discussing. If gravastars truly exist somewhere in the vast cosmic ocean, they represent a fundamental shift in how we understand the relationship between matter, energy, and space-time itself. These aren't merely exotic curiosities tucked away in the margins of theoretical physics. They're potential game changers that could rewrite our understanding of how the universe operates at its most extreme scales. The shell structure of a gravastar presents us with materials science on a scale that dwarfs anything we've ever encountered. Imagine trying to engineer a material that could maintain structural integrity under gravitational forces millions of times stronger than anything on Earth. This isn't just a matter of finding something incredibly strong. It requires matter that exists in quantum states so exotic that our current understanding of materials barely applies. The atoms and molecules that make up everything in our familiar world would be crushed to nothingness long before reaching the densities required for gravastar formation. Instead, these shells must be composed of quantum fields themselves, configurations of energy and momentum that exist independently of conventional particles. It's matter made from the very fabric of spacetime, woven into structures that can withstand forces that would tear apart atomic nuclei as easily as you might separate grains of sand. Within this exotic shell, quantum mechanics operates according to rules that seem almost alien compared to the gentle quantum effects we observe in laboratory experiments. The uncertainty principle, normally confined to the microscopic realm, suddenly becomes relevant on astronomical scales. Virtual particles, those ghostly fluctuations that normally exist for impossibly brief moments, become permanent features of the gravastar's structure. This amplification of quantum effects creates a bridge between the microscopic and macroscopic worlds that physicists have been seeking for nearly a century. In studying gravastars, we might finally understand how quantum mechanics and general relativity can work together rather than existing as separate, incompatible descriptions of reality. These objects could be the Rosetta Stone that finally allows us to decode the unified language of physics. The energy scales involved in gravastar physics are almost beyond comprehension. A typical gravastar might contain the mass of several suns, all compressed into a region smaller than a city. The energy density within its exotic matter shell would exceed that found in the cores of the most massive stars by factors of millions or billions. Yet this energy exists in a state of perfect balance, neither expanding outward nor collapsing inward. This balance isn't static, like a ball sitting at the bottom of a valley. It's dynamic, constantly maintained through quantum processes that operate faster than the speed of light within the shell itself. Information and energy flow through the exotic matter in patterns that create a kind of cosmic metabolism, a continuous dance of creation and annihilation that keeps the entire structure stable. The timeframes over which gravastars operate challenge our human perspective on permanence and change. These objects might maintain their exotic structure for periods longer than the current age of the universe, yet they remain fundamentally temporary configurations. They exist in what physicists call false vacuum states, appearing stable but always possessing the potential to transition into more conventional forms. The decay of a gravastar would be among the most energetic events possible in our universe. When the delicate balance finally fails, the exotic matter shell would collapse in milliseconds, releasing energy equivalent to the complete annihilation of several solar masses. The resulting explosion would outshine entire galaxies, creating gravitational waves so powerful they would ripple through spacetime itself, carrying news of the event to observers billions of light-years away. But even before such catastrophic transitions, gravastars might leave subtle fingerprints on the cosmic environment around them. The exotic matter in their shells interacts with quantum fields in ways that create tiny but detectable distortions in space and time. These distortions could accumulate over millions of years, creating patterns in the cosmic microwave background radiation that we might already have observed without recognizing their significance. The search for these signatures requires us to look at familiar data with completely new eyes. Every gravitational wave detection, every observation of matter spiraling into what we assume are black holes, every measurement of space-time curvature around massive objects becomes a potential clue about whether we're seeing conventional physics or something far more exotic. The mathematical tools required to analyze gravastar physics push our computational capabilities to their absolute limits. Simulating the behavior of exotic matter under extreme gravitational conditions requires solving equations so complex that even our most powerful supercomputers can only approximate their solutions. Each calculation reveals new layers of complexity, new ways that quantum mechanics and gravity can interact to create phenomena we never imagined. These computational challenges aren't merely technical obstacles to be overcome. They represent fundamental limitations in how we can understand objects that exist at the intersection of multiple physical theories. The mathematics of gravastars exists in a realm where small changes in initial conditions can lead to dramatically different outcomes, where chaos theory and quantum uncertainty combine to create a landscape of possibilities so rich that we may never fully explore it. Yet within this mathematical complexity lie hints of deeper simplicities. Some physicists suspect that gravastars might be examples of more general principles that govern how matter and energy organize themselves under extreme conditions. If we can understand these principles, we might discover that gravastars are just one member of an entire family of exotic objects that populate the universe. The observational search for gravastars requires us to develop new techniques for distinguishing between objects that appear nearly identical from a distance. The differences between a gravastar and a black hole of equal mass are subtle, requiring measurements of unprecedented precision and theoretical models of extraordinary sophistication. It's like trying to determine whether a distant light is a candle or a laser by analyzing the color of individual photons. Current gravitational wave detectors have opened new windows into the most violent events in the universe, allowing us to observe the collisions of massive compact objects with exquisite detail. Each detection carries information about the internal structure of the colliding objects, encoded in the precise pattern of space-time ripples they create. Hidden within this data might be the signatures we need to distinguish gravastars from their more conventional cousins. The next generation of gravitational wave observatories will possess sensitivities that dwarf current instruments, capable of detecting the subtle echoes that might reveal hollow interiors rather than singular points. These future observations might finally provide the evidence needed to confirm whether gravastars exist anywhere in our cosmic neighborhood. But perhaps the most profound aspect of gravastar theory isn't what it tells us about these exotic objects themselves, but what it reveals about the nature of scientific discovery. These possibilities were always present in Einstein's equations, waiting patiently for someone to recognize their significance. They remind us that the universe contains mysteries we haven't even learned to ask questions about yet. The journey from mathematical possibility to physical reality is often longer and more complex than we initially anticipate. Many theoretical predictions require decades or centuries before technology advances sufficiently to test them. Gravastars might follow this same pattern, existing for now as beautiful mathematical constructs that await future observations to determine their physical relevance. Yet even in their current theoretical state, gravastars serve an important purpose in expanding our conception of what's possible. They challenge us to think beyond the familiar categories of stars and black holes, to consider that the universe might be populated by objects so strange that we lack adequate language to describe them. They remind us that reality is under no obligation to conform to our expectations about how things should behave. As we stand at the edge of this cosmic mystery, peering into theoretical realms that stretch our understanding to its limits, we find ourselves confronting questions that reach far beyond the specific physics of gravastars. These objects force us to examine our most basic assumptions about the nature of existence itself, about the relationship between the possible and the actual, about the role of consciousness in a universe that seems designed to surprise us at every turn. The story of gravastars is still being written, each new theoretical development adding chapters to a narrative that began with simple questions about the nature of gravitational collapse. Where this story leads us remains unknown, but the journey itself continues to reveal new wonders about the cosmos we inhabit. In the gentle darkness of space, surrounded by mysteries we're only beginning to fathom, gravastars represent one more reminder that the universe is far stranger and more beautiful than we ever dared to imagine. The mathematics that govern gravastar formation reveal patterns so intricate they seem almost artistic in their complexity. Each equation tells a story of balance and tension, of forces so precisely calibrated that the slightest deviation would transform these exotic objects into something entirely different. It's as if the universe has composed a symphony where every note must be played with perfect pitch, or the entire composition collapses into chaos. When physicists first began exploring these mathematical landscapes, they discovered something remarkable about the parameter space where gravastars can exist. It's incredibly narrow, a thin slice of possibility sandwiched between regions where conventional stars and black holes dominate. This suggests that if gravastars exist at all, they represent a kind of cosmic fine-tuning, objects that emerge only when conditions align with extraordinary precision. The formation process itself would be a delicate dance between competing forces that operate on timescales ranging from microseconds to millions of years. As a massive star approaches the end of its life, the nuclear reactions that have sustained it for eons begin to falter. The outward pressure of radiation that has balanced gravity for so long starts to weaken, setting the stage for what could become either conventional collapse or something far more exotic. In those final moments before gravitational collapse becomes irreversible, quantum effects in the vacuum itself might suddenly become macroscopically important. The virtual particles that normally exist as barely detectable fluctuations could amplify into real, measurable forces. It's a process that exists at the boundary between the quantum and classical worlds, where the rules of physics themselves undergo a kind of phase transition. Imagine witnessing such an event from a safe distance, watching as a star several times more massive than our Sun approaches its final moments. The outer layers would begin their inward fall, accelerating to significant fractions of the speed of light as they plunge toward the stellar core. Temperature and pressure would rise to levels that dwarf anything found elsewhere in the universe, creating conditions so extreme that space and time themselves begin to behave in unfamiliar ways. But then, at precisely the moment when conventional physics predicts the formation of an event horizon, something extraordinary might happen instead. The quantum vacuum itself could suddenly become an active participant in the collapse, creating pressures that halt the infall just before the point of no return. The collapsing matter would freeze at the threshold of black hole formation, suspended in a state that defies our everyday understanding of how gravity works. This quantum intervention wouldn't be violent or dramatic in the way we might imagine. There would be no explosion, no sudden burst of energy to mark the transition. Instead, it would be subtle, a gentle shifting of the fundamental forces that shape reality. The dying star would simply choose a different path through the space of possibilities, one that leads to exotic stability rather than singular collapse. The resulting object would appear deceptively familiar from the outside. Its gravitational field would bend light and warp space-time with the same intensity as a black hole of equivalent mass. Spacecraft approaching from a distance would follow identical trajectories, their instruments detecting the same redshift effects and tidal forces. Only the most sensitive measurements might reveal the subtle differences that distinguish a gravastar from its more conventional cousin. These differences lie in the details of how these objects interact with their environments over extremely long timescales. While a black hole grows steadily as it accretes matter from its surroundings, a gravastar's mass would remain essentially constant. The exotic matter in its shell cannot be compressed further, and new material falling toward the object would interact with the shell in ways that might produce distinctive signatures. The accretion process around a gravastar could create patterns of radiation that carry information about the object's internal structure. As matter spirals inward toward what appears to be an event horizon, it might encounter the exotic matter shell and undergo interactions that produce characteristic spectral lines or gravitational wave echoes. These signatures would be subtle, requiring years of careful observation to distinguish from the natural variations in black hole accretion. The theoretical framework that describes these interactions pushes our understanding of quantum field theory into uncharted territory. The exotic matter that comprises a gravastar's shell exists in quantum states that have no analogues in terrestrial physics. These aren't simply highly compressed versions of familiar materials, but entirely new phases of matter that emerge only under the most extreme conditions imaginable. Working with such exotic states requires mathematical tools that didn't exist when Einstein first formulated his theory of general relativity. Modern physicists must combine insights from string theory, loop quantum gravity, and other cutting-edge approaches to even begin describing how these materials might behave. Each calculation reveals new complexities, new ways that quantum mechanics can manifest on astronomical scales. The energy densities within a gravastar's shell would exceed those found in atomic nuclei by factors of millions or billions. Yet this energy exists in a state of perfect equilibrium. neither radiating away nor concentrating further. The quantum fields that make up the exotic matter exist in configurations that are simultaneously stable and metastable, capable of maintaining their structure for cosmological timescales while retaining the potential for dramatic transitions. This duality between stability and instability is one of the most fascinating aspects of Gravastar physics. These objects represent solutions to Einstein's equations that exist in a kind of mathematical twilight zone, neither fully stable nor obviously unstable. They persist through a delicate balance of forces that operates according to principles we're still learning to understand. The interior of a Gravastar presents us with a region of spacetime so exotic that it challenges our basic concepts of emptiness and substance. The negative pressure that fills this hollow core isn't simply the absence of matter, but rather a manifestation of quantum fields in highly unusual states. Virtual particles become real through the sheer intensity of the gravitational field, creating a kind of matter that pushes outward rather than inward. This isn't the familiar vacuum of interstellar space, where virtual particles briefly flicker into existence before annihilating each other. Instead, it's a realm where the uncertainty principle operates on macroscopic scales, where the quantum foam of spacetime becomes visible to classical observers. The very concepts of particle and wave, of something and nothing, lose their usual meanings in this strange environment. The philosophical implications of such spaces stretch far beyond physics into questions about the nature of existence itself. If empty space can exert pressure, if nothingness can push back against the weight of stellar matter, then what do we mean when we talk about the vacuum? These objects force us to reconsider our most basic assumptions about what it means for something to be real. The boundary between the exotic matter shell and the negative pressure interior represents one of the most unusual interfaces in all of physics. Here, matter that exists in quantum states unknown to terrestrial science meets space-time that curves in directions forbidden by classical intuition. The transition between these regions would be smooth on mathematical grounds, yet it represents a boundary between fundamentally different phases of reality. Crossing this boundary from the outside would be like passing from one universe into another, each governed by subtly different laws of physics. The exotic matter shell exists in a realm where quantum mechanics dominates, while the interior operates according to principles that blend general relativity with vacuum dynamics in ways we're only beginning to explore. An observer making such a journey would witness the fundamental forces of nature shifting their relative importance as they moved between these regions. The observational signatures of such transitions might be detectable through careful study of how matter behaves near these objects. Particles approaching a gravastar would experience forces that differ subtly from those around a conventional black hole. These differences would be small, perhaps detectable only through statistical analysis of many observations, but they could provide the evidence needed to distinguish between these exotic possibilities and more familiar alternatives. The search for such signatures requires us to develop new theoretical frameworks for understanding how quantum fields behave under extreme gravitational conditions. The mathematics involved pushes beyond the standard model of particle physics into realms where our current theories provide only approximate guidance. Each calculation reveals new layers of complexity, new ways that the fundamental forces can combine to create phenomena we never anticipated. Current observations of objects we assume to be black holes might already contain evidence for Gravastar-like behavior, hidden in data we haven't yet learned to properly analyze. The gravitational waves detected by instruments like LIGO carry information about the internal structure of colliding objects, encoded in subtle variations in frequency and amplitude that require sophisticated analysis to decode. Within these signals might lie the proof we need to confirm whether these exotic alternatives to black holes actually exist. The next generation of gravitational wave detectors will possess sensitivity levels that could finally resolve the question of whether gravastars populate our universe. These instruments will be capable of detecting the echoes and reverberations that might distinguish hollow objects from singular points, providing observational tests of theoretical predictions that have existed in mathematical form for decades. But even as we develop the tools needed to search for these exotic objects, new theoretical possibilities continue to emerge from the fertile ground of general relativity. Gravastars might represent just one example of a broader class of exotic compact objects, each with its own distinctive properties and observational signatures. The universe might be populated by an entire menagerie of strange objects that exist in the grey areas between conventional stars and black holes. These possibilities remind us that our current understanding of cosmic architecture might be profoundly incomplete. We've built our models of stellar evolution and galactic dynamics around the assumption that massive objects must eventually collapse into black holes. But this assumption might reflect the limitations of our imagination rather than the constraints of physical law. The universe could be far stranger and more diverse than we've dared to consider. As we continue our exploration of these cosmic mysteries, we find ourselves standing at the threshold of discoveries that could fundamentally alter our understanding of reality itself. The gentle mathematics that describes gravastars contains within it the potential to revolutionize how we think about matter, energy, space, and time. These aren't merely exotic curiosities tucked away in the corners of theoretical physics, but possible glimpses into the deeper structures that govern our universe. In the vast darkness that surrounds us, filled with objects we're only beginning to understand, gravastars represent one more reminder that the cosmos refuses to be confined by our expectations. They exist in that beautiful realm between the known and unknown, between the possible and impossible, where mathematics and imagination converge to reveal truths stranger than any fiction we could devise. The journey into Gravastar physics takes us to places where our familiar intuitions about cause and effect begin to break down completely. These objects exist at the intersection of multiple physical theories, each contributing its own layer of complexity to an already bewildering picture. As we delve deeper into their theoretical structure, we encounter phenomena that seem to belong more in the realm of pure mathematics than in the physical universe we think we know. Consider the temporal aspects of gravastar formation and evolution. While a conventional star lives and dies according to timescales we can comprehend, burning through its nuclear fuel over millions or billions of years before finally succumbing to gravitational collapse, gravastars operate according to a completely different temporal logic. Their exotic matter shells exist in states that are essentially timeless from certain perspectives, maintaining their structure through quantum processes that unfold faster than light itself. This creates a paradox that challenges our understanding of how information and causality propagate through spacetime. Within the shell of a gravastar, Quantum correlations can establish themselves instantaneously across regions that would normally require finite time for light to traverse. It's as if the exotic matter exists partially outside the normal flow of time, connected to itself through channels that bypass the usual constraints of special relativity. The implications extend far beyond the objects themselves into the very foundations of how we understand the relationship between space and time. If matter can exist in states that transcend temporal limitations, then our entire framework for thinking about cosmic evolution might need fundamental revision. The universe might contain pockets where different regions experience time at dramatically different rates, or where the usual ordering of cause and effect becomes meaningless. These temporal anomalies would create observable consequences that ripple outward from gravastars like stones thrown into the cosmic pond. Nearby matter would experience subtle but measurable distortions in its own temporal flow, creating patterns in stellar motion and galactic structure that could serve as signatures of these exotic objects. The very fabric of spacetime around a gravastar would carry the imprint of its unusual internal dynamics. The quantum mechanics that govern gravastar interiors operate according to principles that push the boundaries of what we consider physically reasonable. The uncertainty principle, normally confined to microscopic scales, becomes amplified to astronomical proportions within these objects. Virtual particles that should exist only for infinitesimal moments become permanent features of the space-time geometry, their ghostly presence transformed into measurable forces capable of supporting the weight of collapsed stars. This amplification of quantum effects creates a bridge between the microscopic realm of particle physics and the macroscopic world of astrophysics that physicists have been seeking for decades. In studying gravastars, we might finally understand how the probabilistic nature of quantum mechanics gives rise to the apparently deterministic behavior of large-scale cosmic structures. These objects could be the key to unifying our understanding of physics across all scales. The energy flows within a gravastar create patterns of extraordinary complexity and beauty. Unlike the relatively simple nuclear reactions that power conventional stars, the processes that maintain gravastar stability involve intricate dances between quantum fields that exist in highly excited states. Energy cascades through the exotic matter shell in ways that create resonances and harmonics reminiscent of musical instruments, but operating on scales that dwarf entire solar systems. These energy patterns might be detectable through careful analysis of the electromagnetic radiation emitted from gravastar environments. While the objects themselves would appear dark to conventional telescopes, the interaction between their exotic matter shells and infalling material could create distinctive spectral signatures. Certain wavelengths of light might be amplified or suppressed in characteristic ways, creating a kind of cosmic fingerprint that could distinguish gravastars from other astrophysical objects. The gravitational fields surrounding gravastars exhibit subtleties that exist at the very limits of our current measurement capabilities. While the overall curvature of spacetime would match that of a black hole with equivalent mass, tiny deviations from perfect spherical symmetry might reveal the presence of internal structure. These deviations would be incredibly small, perhaps detectable only through decades of careful observation or through the accumulated effects of many gravitational interactions. The challenge lies in developing theoretical frameworks sophisticated enough to predict exactly what these signatures should look like. The mathematics involved requires solving systems of equations so complex that even approximate solutions push our computational resources to their limits. Each calculation reveals new layers of detail, new ways that quantum mechanics and general relativity can combine to create phenomena that neither theory predicts in isolation. Modern supercomputers struggle to simulate even simplified versions of Gravastar dynamics, their processors overwhelmed by the sheer complexity of tracking quantum fields under extreme gravitational conditions. Yet these computational challenges aren't merely technical obstacles to be overcome through better hardware. They represent fundamental limitations in how we can understand systems that exist at the intersection of multiple physical theories. The mathematical tools required to describe Gravastar physics draw from branches of mathematics that were developed for entirely different purposes. Topology, differential geometry, quantum field theory, and statistical mechanics all contribute essential insights, yet none provides a complete picture by itself. Understanding these objects requires a synthesis of mathematical techniques that spans nearly every area of theoretical physics. This mathematical complexity isn't accidental, but reflects something deeper about the nature of reality at extreme scales. When matter and energy are compressed to densities that approach the fundamental limits set by quantum mechanics and general relativity, the simple distinctions that organize our everyday understanding of physics begin to blur. Particles and waves, matter and energy, space and time all become aspects of a more fundamental unity that our current theories can only approximate. The philosophical implications of Gravastar theory extend far beyond physics into questions about the nature of existence itself. These objects force us to confront the possibility that reality might be far more fluid and malleable than our everyday experience suggests. If space and time can be warped into configurations that create stable, hollow regions filled with negative pressure, then what other possibilities might exist that we haven't yet imagined? The boundary conditions that determine whether a collapsing star becomes a gravastar rather than a black hole might depend on factors we don't yet understand or even recognize as important. Tiny variations in the quantum state of the stellar matter, subtle correlations between distant parts of the collapsing system, or influences from quantum fields that permeate all of space might all play crucial roles in determining the final outcome. This sensitivity to initial conditions creates a kind of cosmic butterfly effect, where microscopic variations in quantum states can lead to macroscopic differences in the resulting objects. The universe might be populated by both conventional black holes and exotic gravastars, their relative abundances determined by quantum processes that operate below the threshold of direct observation. The search for observational evidence of gravastars requires us to think carefully about what constitutes proof in a realm where direct experimentation is impossible. We cannot create these objects in laboratory settings or manipulate their properties to test specific predictions. Instead, we must rely on careful observation of natural phenomena, looking for patterns that distinguish one theoretical possibility from another. Current gravitational wave astronomy has opened new windows into the most extreme environments in the universe, allowing us to observe the final moments of massive compact objects as they spiral into each other and merge. Each detection carries encoded information about the internal structure of the colliding objects, hidden in the precise pattern of spacetime ripples they create as they dance their final cosmic dance. The gravitational waves produced by gravastar collisions would carry distinctive signatures that reflect their hollow internal structure. Instead of the clean, simple waveforms expected from black hole mergers, gravastar collisions might produce complex patterns of echoes and reverberations as gravitational waves bounce around inside the exotic matter shells. These signatures would be subtle, requiring sophisticated data analysis techniques to extract from the noise. But they could provide definitive proof of gravastar existence. The next generation of gravitational wave detectors will possess sensitivities that exceed current instruments by orders of magnitude, capable of detecting variations in spacetime geometry smaller than 1,000th of a proton width. With such extraordinary precision, the subtle differences between gravastar and black hole collisions might finally become observable, allowing us to determine whether these exotic alternatives to conventional collapse actually exist in our universe. But perhaps most remarkably, the study of gravastars is teaching us that the universe might be far more creative in its solutions to the problem of extreme gravity than we ever anticipated. These objects represent just one possibility among many that emerge from the fertile mathematical landscape of general relativity. As our computational tools become more sophisticated and our observational capabilities more sensitive, we might discover an entire ecosystem of exotic, compact objects, each with its own distinctive properties and formation mechanisms. The cosmos surrounding us might be populated by objects so strange that we lack adequate vocabulary to describe them, phenomena that exist in the grey areas between our conventional categories of understanding. Gravastars remind us that reality is under no obligation to conform to our expectations about how things should behave, that the universe contains mysteries we haven't even learned to ask questions about yet. In the gentle darkness of space, where light itself becomes a prisoner of gravity and time flows at rates that depend on position and velocity, these exotic possibilities wait patiently for discovery. They exist in that beautiful realm between the known and unknown, between mathematics and observation, where human curiosity encounters the deepest mysteries of existence itself. As we continue our journey through these cosmic enigmas, we find ourselves confronting questions that reach far beyond the specific physics of any particular type of object. We're exploring the very foundations of how reality organizes itself at its most fundamental level, how the simple laws we discover in terrestrial laboratories give rise to phenomena of breathtaking complexity and beauty on cosmic scales. The story of Gravastars is ultimately a story about the power of mathematics to reveal possibilities hidden within the structure of physical law, about the endless creativity of a universe that refuses to be constrained by our limited imagination. In their exotic shells of quantum matter and their hollow cores of negative pressure spacetime, we glimpse reflections of truths about reality that we're only beginning to understand. The search for gravastars has become one of the most fascinating detective stories in modern astrophysics, where the clues exist in the subtle whispers of spacetime itself. Every gravitational wave detection, every observation of matter spiraling into what we assume are black holes, every measurement of how light bends around massive objects becomes a potential piece of evidence in this cosmic mystery. The challenge lies not in finding something dramatically different, but in recognizing the delicate signatures that distinguish the exotic from the familiar. Consider the extraordinary precision required to detect these differences. We're looking for variations so small they exist at the very threshold of what our instruments can measure. It's like trying to distinguish between two musical notes that differ by less than 1,000th of a semitone, played by orchestras billions of light years away. The human ear would never notice such subtle differences, yet the mathematical analysis of gravitational waves might finally give us the sensitivity we need. The accretion disks that form around these objects present another avenue for discovery. When matter spirals into a conventional black hole, it follows predictable patterns as it crosses the event horizon and disappears forever. But around a gravastar, that same matter would encounter something fundamentally different. Instead of vanishing into a singular point, it would interact with the exotic matter shell in ways that could produce distinctive spectral signatures. These interactions would be like cosmic conversations, with the infalling matter and the gravastar's shell exchanging energy in patterns that carry information about the object's internal structure. Certain wavelengths of radiation might be enhanced or suppressed, creating fingerprints in the electromagnetic spectrum that could reveal the presence of a physical surface rather than an event horizon. The challenge lies in developing theoretical models sophisticated enough to predict exactly what these signatures should look like. The thermal properties of gravastars present another fascinating puzzle. While black holes are predicted to emit Hawking radiation at incredibly low temperatures, gravastars might exhibit entirely different thermal behaviors. The exotic matter in their shells could interact with quantum fields in ways that produce characteristic patterns of emission, creating thermal signatures that distinguish them from their more conventional cousins. These thermal effects would be extraordinarily subtle, requiring observations over decades or centuries to accumulate enough data for meaningful analysis. But the patience required for such studies reflects a deeper truth about astronomical research. The universe operates on timescales that dwarf human experience, revealing its secrets only to those willing to think in terms of generations rather than years. The stability analysis of gravastars reveals mathematical landscapes of breathtaking complexity. These objects exist in what physicists call local minima of the energy landscape, stable against small perturbations, but vulnerable to larger disturbances. It's like balancing a marble in a shallow depression on a hillside. Small nudges will cause it to roll back to its equilibrium position, but a sufficiently large disturbance could send it tumbling down the slope into an entirely different configuration. This metastability creates fascinating possibilities for gravastar evolution. These objects might maintain their exotic structure for billions of years, outlasting the stars that gave birth to them, only to suddenly transition into conventional black holes when some critical threshold is finally crossed. The trigger for such transitions could be anything from the accumulation of infalling matter to interactions with passing gravitational waves. The transition process itself would be among the most spectacular events imaginable. As the delicate balance that maintains the gravastar's structure finally fails, the exotic matter shell would collapse in milliseconds, releasing energies that could outshine entire galaxies. The gravitational waves produced by such events would carry the signature of this dramatic transformation across billions of light years, announcing to distant observers that another exotic object has surrendered to more conventional physics. These catastrophic transitions might explain some of the most energetic phenomena we observe in the universe. Gamma-ray bursts, those mysterious flashes of radiation that briefly outshine everything else in the cosmic sky, could potentially result from gravastar collapses. The energy scales involved would certainly be sufficient to power such events, and the theoretical predictions for the radiation patterns might match what we actually observe. But even more intriguingly, the study of gravastars has opened our eyes to the possibility that the universe might contain entire families of exotic objects that we've never seriously considered. If quantum effects can halt gravitational collapse at one particular density, why not at others? There might be a whole spectrum of exotic, compact objects, each stabilized by different quantum mechanisms operating at different scales. These possibilities stretch our imagination in directions we never anticipated. We might share the universe with objects whose internal structure defies every intuition we've developed about how matter and energy behave under extreme conditions. Some might be hollow like gravastars, while others could contain multiple shells of different exotic matter phases, creating nested structures of extraordinary complexity. The formation mechanisms for such objects would require us to completely rethink our understanding of stellar evolution. The life cycles of massive stars might branch into multiple possible endpoints, with the final outcome determined by subtle quantum processes that we're only beginning to understand. The universe might be far more creative in its solutions to the problem of extreme gravity than our current theories suggest. The observational challenges posed by this diversity of possibilities are staggering. How do we distinguish between dozens of different types of exotic objects when they all produce nearly identical gravitational effects? The answer lies in developing increasingly sophisticated analysis techniques that can extract meaning from the subtlest variations in observational data. Machine learning algorithms are beginning to play crucial roles in this endeavor, trained on theoretical predictions to recognize patterns that human analysts might miss. These artificial intelligence systems can process vast amounts of data, searching for correlations and anomalies that could reveal the presence of exotic physics. It's a new kind of astronomy, where computers help us see patterns hidden in the cosmic noise. The philosophical implications of this search extend far beyond the discovery of new types of astronomical objects. We're essentially asking whether the universe contains phenomena that transcend our current understanding of physical law. The existence of gravastars would demonstrate that reality operates according to principles we've barely begun to explore, that the mathematical framework of general relativity contains possibilities we never seriously considered. This connects to deeper questions about the nature of scientific discovery itself. How often do we miss important phenomena because they don't fit our preconceived notions about how the universe should behave? The history of science is filled with examples of discoveries that were initially dismissed as impossible, only to be later recognized as revolutionary insights into the workings of nature. The search for gravastars reminds us to remain open to possibilities that challenge our assumptions. These objects might exist in the vast darkness between the stars, their exotic properties hidden behind gravitational fields that mimic those of conventional black holes. They could be common features of the cosmic landscape, or they might be incredibly rare, forming only under the most extraordinary circumstances. The theoretical frameworks we've developed to describe these objects continue to evolve as our understanding deepens. Each new calculation reveals additional layers of complexity, new ways that quantum mechanics and general relativity can combine to create phenomena that neither theory predicts in isolation. The mathematics itself seems to be teaching us about possibilities we never imagined. Working in this field requires a delicate balance between mathematical rigor and physical intuition. The equations that describe Gravastar physics exist at the very limits of what we can solve analytically, often requiring numerical approximations that push our computational resources to their breaking points. Yet within these complex calculations lie insights that could fundamentally alter our understanding of how the universe works at its most extreme scales. The energy scales involved in Gravastar physics dwarf anything we encounter in terrestrial experience. The forces that maintain the stability of these exotic matter shells operate with intensities that exceed those found in atomic nuclei by factors of millions or billions. Yet these enormous energies exist in states of perfect equilibrium, neither expanding outward nor collapsing inward, maintained through quantum processes that operate according to principles we're still learning to understand. This equilibrium isn't static, but dynamic, constantly maintained through intricate feedback mechanisms that operate faster than light itself within the exotic matter shell. Information and energy flow through these structures in patterns that create a kind of cosmic metabolism, a continuous dance of quantum creation and annihilation that keeps the entire system stable against the crushing weight of its own gravity. The temporal aspects of this stability are particularly fascinating. From our external perspective, Gravastars might maintain their structure for periods longer than the current age of the universe. Yet from the perspective of the exotic matter itself, existing in regions where time flows differently due to extreme gravitational fields, the maintenance processes might unfold according to entirely different rhythms. This relativity of timescales creates paradoxes that challenge our understanding of how complex systems can maintain themselves over cosmic periods. The quantum processes that stabilize Gravastars operate according to their own internal clocks, which might run faster or slower than the universal time we measure from our distant vantage point. It's a reminder that time itself is far more flexible and context-dependent than our everyday experience suggests. The study of these temporal effects has implications that extend far beyond Gravastar physics into our understanding of how information and causality propagate through curved spacetime. If exotic matter can exist in states where different regions experience time at dramatically different rates, then our entire framework for thinking about cosmic evolution might need fundamental revision. As we continue to explore these theoretical landscapes, we find ourselves constantly surprised by the richness of possibilities that emerge from the mathematical structure of general relativity. Each new calculation opens doorways to phenomena we never anticipated, revealing that the universe might be populated by objects so strange that we lack adequate language to describe them. The search for observational evidence continues with growing sophistication and sensitivity. New generations of gravitational wave detectors are being designed specifically to search for the subtle signatures that might distinguish exotic objects from their conventional counterparts. Space-based observatories will soon possess capabilities that exceed anything currently available, allowing us to probe the most extreme environments in the universe with unprecedented precision. But perhaps most importantly, the journey into Gravastar physics is teaching us something profound about the nature of scientific inquiry itself. We're learning that the universe contains mysteries we haven't even learned to ask questions about yet, phenomena that exist in the spaces between our current theories and observations. The gentle mathematics that describes these exotic possibilities serves as a reminder that reality is far stranger and more beautiful than we ever dared to imagine. In the vast cosmic ocean that surrounds us, filled with objects we're only beginning to understand, Gravastars represent one more frontier in our endless quest to comprehend the deepest structures of existence. They exist in that beautiful realm between the possible and impossible, where human curiosity encounters the fundamental mysteries of space, time, matter, and energy in their most extreme manifestations. The cosmic implications of Gravastar physics ripple outward through every aspect of our understanding, touching on questions that philosophers and scientists have pondered for centuries. If these exotic objects truly exist, they represent something far more profound than merely another type of astronomical body. They embody the universe's capacity to surprise us, to reveal solutions to physical problems that we never dreamed were possible. Consider what it means for matter to exist in the quantum states that comprise a Gravastar's shell. These aren't simply highly compressed versions of familiar materials, but entirely new phases of existence that emerge only when the fundamental forces of nature are pushed to their absolute limits. The atoms and molecules that make up everything in our familiar world would cease to have meaning long before reaching such extreme conditions. Instead, the shell consists of quantum fields themselves, patterns of energy and probability that exist independently of conventional particles. It's matter made from the very fabric of spacetime, woven into structures that can withstand gravitational forces so intense they would tear apart atomic nuclei as easily as you might separate grains of sand. The mathematical description of such states requires us to abandon many of our comfortable assumptions about what matter actually is. Within this exotic shell, the familiar boundaries between different types of particles begin to blur completely. Electrons, protons, neutrons, and all the other building blocks of ordinary matter lose their individual identities, merging into collective quantum states that behave according to rules we're only beginning to comprehend. It's as if the universe has discovered a way to compress not just matter, but the very concept of identity itself. The energy densities involved create environments where virtual particles, normally confined to brief quantum fluctuations, become permanent features of the local space-time geometry. The uncertainty principle, usually relegated to microscopic phenomena, suddenly operates on astronomical scales. Quantum mechanics and general relativity, those two pillars of modern physics that have resisted unification for nearly a century, finally meet in a dance of mathematical beauty and physical extremity. This convergence happens not through some abstract theoretical framework, but in the concrete reality of objects that might actually exist somewhere in the vast cosmic darkness. Gravastars could be nature's own laboratories for quantum gravity, places where the deepest questions about the nature of reality play out on scales large enough for us to potentially observe and study. The hollow interior of a Gravastar presents us with space-time configurations so exotic they seem to belong in science fiction rather than serious physics. Here, the vacuum itself becomes an active participant in maintaining the object's structure. The negative pressure that fills this region isn't simply empty space, but a manifestation of quantum fields in states so unusual that they push outward with precisely the right force to balance the inward pull of the exotic matter shell. This negative pressure creates a kind of anti-gravity effect that operates according to principles completely alien to our everyday experience. It's not that gravity itself is reversed, but rather that the quantum properties of empty space become so amplified that they generate forces capable of supporting the weight of collapsed stellar matter. The mathematics describing such states pushes the boundaries of what we consider physically reasonable. Imagine trying to visualize such a space, where the vacuum itself exerts pressure, where nothingness pushes back against the weight of matter. Our brains, evolved to navigate a world of familiar objects and forces, struggle to form mental pictures of such exotic environments. Yet, the equations tell us these configurations are not only possible, but might be inevitable consequences of the laws of physics under sufficiently extreme conditions. The boundary between the exotic matter shell and the negative pressure interior represents one of the most unusual interfaces conceivable in physics. Here, matter existing in quantum states unknown to terrestrial science meets spacetime curved in directions forbidden by classical intuition. The transition between these regions would be mathematically smooth, yet it represents a passage between fundamentally different phases of reality. An observer crossing this boundary would witness the fundamental forces of nature shifting their relative importance in ways that have no parallel in normal experience. The electromagnetic interactions that dominate atomic physics would give way to quantum field effects that operate according to entirely different principles. It would be like stepping from one universe into another, each governed by subtly but crucially different laws of physics. The observational challenges posed by such exotic objects continue to drive innovations in both theoretical physics and experimental technique. Current gravitational wave detectors, already marvels of precision engineering, represent only the beginning of our quest to probe these extreme environments. The next generation of instruments will possess sensitivities that dwarf anything currently available, capable of detecting space-time distortions smaller than 1,000th of a proton width. With such extraordinary precision, the subtle differences between Gravastar and black hole collisions might finally become observable. The gravitational waves produced by these cosmic catastrophes carry encoded information about the internal structure of the colliding objects, hidden in patterns so delicate they require years of careful analysis to decode. Each detection becomes a cosmic archaeology project, revealing secrets about the nature of matter and space-time under the most extreme conditions imaginable. The theoretical frameworks we use to analyze such data continue to evolve at a breathtaking pace. Machine learning algorithms, trained on thousands of simulated collisions, are learning to recognize patterns that human analysts might never notice. These artificial intelligence systems can process vast amounts of information, searching for correlations and anomalies that could reveal the presence of exotic physics hidden in the cosmic noise. But even as our observational capabilities grow more sophisticated, new theoretical possibilities continue to emerge from the fertile mathematical landscape of general relativity. Gravastars might represent just the tip of an iceberg, one example of a vast family of exotic objects that populate the universe in ways we're only beginning to imagine. The parameter space of possible solutions to Einstein's equations is so rich that we might spend centuries exploring all its implications. Some of these possibilities stretch our conception of what objects can even exist. There might be configurations where multiple exotic matter shells nest within each other like cosmic Russian dolls, each maintained by different quantum mechanisms operating at different scales. Other solutions might describe objects that exist partially outside normal spacetime, connected to our universe through portals so small they escape direct detection. The formation mechanisms for such exotic objects would require us to completely rethink stellar evolution. The death throes of massive stars might branch into dozens of possible endpoints, each determined by quantum processes so subtle that tiny variations in initial conditions lead to dramatically different outcomes. The universe might be far more creative in its solutions to gravitational collapse than our current theories suggest. These possibilities carry profound implications for our understanding of cosmic history. If exotic objects like Gravastars have been forming throughout the universe's evolution, they might have played crucial roles in shaping the large-scale structure we observe today. Their gravitational influence could have guided the formation of galaxies and galaxy clusters in ways we've never considered. The energy released during Gravastar formation or collapse events might explain some of the most mysterious phenomena in astrophysics. Gamma-ray bursts, those brief but incredibly powerful flashes of radiation that occasionally light up the cosmic sky, could potentially result from the catastrophic transitions of these exotic objects. The energy scales involved would certainly be sufficient to power such events, and the theoretical predictions for radiation patterns might match what we actually observe. But perhaps most significantly, the study of Gravastars is forcing us to confront fundamental questions about the nature of scientific knowledge itself. How do we develop confidence in theoretical predictions about phenomena so extreme that they might never be directly testable? What constitutes evidence in realms where controlled experimentation is impossible and where the relevant timescales dwarf human civilization? These epistemological challenges reflect deeper truths about the relationship between mathematics and physical reality. The equations that describe Gravastars emerge from pure mathematical exploration of general relativity, yet they might correspond to actual objects existing somewhere in the cosmic darkness. This suggests a profound connection between abstract mathematical structures and concrete physical phenomena that we're only beginning to understand. The mathematical tools required to explore these possibilities continue to push the boundaries of what we can calculate and comprehend. Each new technique reveals additional layers of complexity, new ways that quantum mechanics and general relativity can combine to create phenomena that neither theory predicts in isolation. The equations themselves seem to contain more information about possible realities than we initially realized. Working in this field requires a unique blend of mathematical sophistication and physical intuition. The solutions that describe exotic objects like Gravastars exist in narrow parameter ranges where small changes in assumptions can lead to dramatically different predictions. It's like walking a tightrope suspended over an abyss of mathematical complexity, where every step must be carefully calculated to avoid falling into regions where the physics becomes either trivial or nonsensical. The computational challenges are equally formidable. Simulating the behavior of exotic matter under extreme gravitational conditions requires solving equations so complex that even our most powerful supercomputers can only approximate their solutions. Each calculation reveals new subtleties, new ways that quantum fields can interact with curved spacetime to create stable configurations that classical physics would consider impossible. Yet, within this mathematical complexity lie hints of deeper simplicities. Some physicists suspect that Gravastars might be examples of more general principles, governing how matter and energy organize themselves under extreme conditions. If we can identify these principles, we might discover that exotic objects are far more common than we currently imagine, representing natural solutions to problems posed by the fundamental structure of spacetime itself. The search for these deeper patterns has led to unexpected connections between seemingly unrelated areas of physics. Techniques developed to study black holes in string theory find applications in Gravastar physics. Methods from condensed matter physics provide insights into how exotic matter might behave under gravitational stress. The boundaries between different fields of research are dissolving as we recognize that extreme physics requires a synthesis of all our theoretical tools. This interdisciplinary approach is revealing new perspectives on old problems. Questions about the nature of spacetime that seemed purely academic suddenly become relevant to understanding how the universe creates and maintains its most extreme objects. The relationship between quantum mechanics and gravity, that central unsolved puzzle of theoretical physics, might finally find resolution in the study of exotic compact objects like Gravastars. The philosophical implications extend far beyond physics into questions about the nature of reality itself. If the universe can create objects whose internal structure transcends our current understanding of matter and energy, what does this tell us about the relationship between the possible and the actual? Are we living in a cosmos where mathematical consistency is the only constraint on what can exist? These questions touch on deep issues in the philosophy of science. How do we distinguish between mathematical possibilities and physical realities? What role does observational confirmation play when the phenomena in question exist at the very limits of what we can detect? The study of Gravastars is forcing us to develop new frameworks for thinking about evidence and explanation in contexts where traditional experimental methods don't apply. As we continue this journey through cosmic extremes, we find ourselves repeatedly confronted by the inadequacy of our everyday language to describe what we're discovering. Words like matter, energy, space, and time, which serve us well in familiar contexts, begin to lose their precision when applied to objects that exist at the intersection of quantum mechanics and general relativity. We need new vocabulary to match the new realities we're uncovering. The future of Gravastar research lies not just in better observations or more sophisticated theories, but in developing entirely new ways of thinking about the relationship between mathematics and physics. We're learning that the universe might be far more mathematically rich than we ever imagined, containing solutions to physical problems that transcend the categories we use to organize our understanding. In the vast darkness that surrounds us, filled with mysteries we're only beginning to recognize, Gravastars represent one more frontier in our endless quest to comprehend the deepest structures of existence. They remind us that reality refuses to be confined by our expectations, that the cosmos contains surprises we haven't even learned to anticipate. As we stand at the threshold of discoveries that could fundamentally alter our understanding of space, time, matter, and energy, we find ourselves humbled by the recognition that we've barely begun to explore the true depths of cosmic possibility. The journey deeper into Gravastar physics reveals mathematical landscapes so intricate they seem to pulse with their own hidden rhythms. Each equation unfolds like a cosmic symphony, where every term must harmonize with extraordinary precision, or the entire composition dissolves into mathematical chaos. These aren't simply abstract formulas scribbled on blackboards in university lecture halls. They're blueprints for objects that might actually exist in the vast cosmic ocean surrounding us, waiting patiently to be discovered. When theoretical physicists first began exploring the parameter space where gravastars could potentially form, they discovered something remarkable about the delicate balance required for their existence. The mathematical conditions are so restrictive, so precisely calibrated, that it's almost as if the universe has composed a piece of cosmic poetry where every syllable must be perfectly placed. Change even the smallest variable, and these exotic objects transform into something entirely different. Conventional black holes or neutron stars. This exquisite sensitivity to initial conditions creates what physicists call a fine-tuning problem of extraordinary proportions. The quantum fields that would comprise a gravastar's shell must exist in states so specific that the margin for error approaches zero. It's like trying to balance a needle on its point while standing in a hurricane, where the slightest disturbance sends everything tumbling into more familiar configurations. Yet this apparent fragility might actually reveal something profound about how the universe operates at its deepest levels. Perhaps these extreme requirements aren't obstacles to gravastar formation, but rather natural consequences of the mathematical structure that governs reality itself. The universe might be far more creative in its solutions to physical problems than our limited imagination suggests, finding ways to create stable configurations in parameter ranges we'd never thought to explore. The quantum mechanical processes that would maintain gravastar stability operate according to principles that stretch our understanding of how information and energy can flow through curved spacetime. Within the exotic matter shell, quantum correlations establish themselves across regions that would normally require significant time for light to traverse. It's as if the shell exists partially outside the normal flow of temporal causality, connected to itself through channels that bypass the usual constraints of special relativity. This creates temporal paradoxes that would make even experienced physicists pause and reconsider their basic assumptions about how cause and effect propagate through the cosmos. The maintenance processes that keep a gravastar stable might unfold according to their own internal chronology, operating faster or slower than the universal time we measure from our distant terrestrial vantage point. Time itself becomes relative, not just to motion and gravity, but to the exotic quantum states that define these remarkable objects. The energy flows within a gravastar's shell create patterns of breathtaking complexity that dwarf anything we observe in conventional stellar physics. Unlike the relatively straightforward nuclear fusion that powers ordinary stars, the processes maintaining gravastar equilibrium involve intricate cascades of quantum field interactions that operate on multiple scales simultaneously. Energy dances through the exotic matter in waves and spirals that create resonances reminiscent of cosmic musical instruments, but operating on scales that encompass entire solar systems. These energy patterns might be detectable through careful analysis of the subtle ways gravastars interact with their cosmic environments. While the objects themselves would appear dark to conventional optical telescopes, their exotic matter shells could create distinctive distortions in the quantum vacuum that surrounds them. Virtual particles in nearby regions might be influenced by the shell's unusual properties, creating patterns of quantum foam that carry information about the object's internal structure. The gravitational fields surrounding gravastars exhibit subtleties that exist at the very threshold of our current measurement capabilities. While the overall curvature of spacetime would closely match that produced by a black hole of equivalent mass, tiny deviations from perfect symmetry might reveal the presence of internal structure. These deviations would be incredibly small, perhaps detectable only through the accumulated effects of many gravitational interactions observed over decades or centuries. Current gravitational wave astronomy has opened unprecedented windows into the most extreme environments in the universe, allowing us to observe the final moments of massive compact objects as they spiral into each other in cosmic death dances. Each detection carries encoded information about the colliding object's internal structure, hidden in the precise patterns of spacetime ripples they create during their final orbital decay. The gravitational waves produced by Gravastar mergers would carry distinctive signatures that reflect their hollow internal architecture. Instead of the relatively clean waveforms expected from black hole collisions, Gravastar mergers might produce complex patterns of echoes and reverberations as gravitational waves bounce around inside the exotic matter shells before escaping into the broader cosmos. These signatures would be subtle, requiring sophisticated analysis techniques to extract from the observational noise, but they could provide the definitive evidence we need to confirm whether these exotic alternatives actually populate our universe. The next generation of gravitational wave observatories will possess sensitivities that exceed current instruments by orders of magnitude. These future detectors will be capable of measuring space-time distortions smaller than 1/1000th of a proton width. Precision so extraordinary that it challenges our engineering capabilities and pushes the boundaries of what's physically possible to construct. With such remarkable sensitivity, the delicate differences between exotic object collisions and their conventional counterparts might finally become observable. But even as our observational tools become more sophisticated, the theoretical challenges of understanding Gravastar physics continue to multiply. Each new calculation reveals additional layers of complexity, new ways that quantum mechanics and general relativity can interact to create phenomena that neither theory predicts when considered in isolation. The mathematics pushes beyond the standard models of both particle physics and cosmology into realms where our current theoretical frameworks provide only approximate guidance. The computational requirements for simulating Gravastar dynamics strain even our most powerful supercomputers. Tracking the behavior of quantum fields under extreme gravitational conditions requires solving systems of equations so complex that approximate solutions often represent the best we can achieve. Each computational run reveals new subtleties in how exotic matter responds to gravitational stress, new instabilities that might develop over astronomical timescales, new pathways for these objects to evolve or decay. These computational challenges aren't merely technical obstacles to be overcome through better hardware and more efficient algorithms. They represent fundamental limitations in how we can understand systems that exist at the intersection of multiple physical theories, where small changes in initial conditions can cascade into dramatically different outcomes through processes we're only beginning to comprehend. The stability analysis of Gravastars reveals mathematical terrain of extraordinary richness and complexity. These objects exist in what mathematicians call local minima of the energy landscape, stable against small perturbations, but potentially vulnerable to larger disturbances. The metaphor of a marble balanced in a shallow depression becomes inadequate when applied to systems where the landscape itself can change in response to the marble's position. This dynamic stability creates fascinating possibilities for Gravastar evolution over cosmic timescales. These objects might maintain their exotic structure for billions of years, outlasting the galaxies that contain them, only to suddenly transition into conventional black holes when some critical threshold is finally exceeded. The triggers for such transitions could be anything from the gradual accumulation of infalling matter to interactions with passing gravitational waves or encounters with other exotic objects. The collapse process itself would represent one of the most energetic events conceivable in our universe. When the delicate quantum balance finally fails, the exotic matter shell would implode in microseconds, releasing energies that could briefly outshine entire galactic clusters. The gravitational waves produced by such catastrophic transitions would propagate across billions of light years, carrying the distinctive signature of exotic matter collapse to distant observers who might never otherwise know these objects existed. These dramatic events might already be occurring somewhere in the vast cosmic expanse, their signals racing toward us at the speed of light through the darkness between galaxies. Future gravitational wave detectors might catch these cosmic death screams, providing our first direct evidence that the universe contains objects whose internal structure transcends our current understanding of how matter and energy can organize themselves under extreme conditions. But perhaps even more intriguingly, the study of Gravastar physics is revealing connections to other exotic phenomena that we observe throughout the cosmos. The quantum processes that might stabilize these objects could be related to the mechanisms that drive cosmic inflation, that mysterious period of exponential expansion that shaped the universe during its earliest moments. The same mathematical frameworks that describe exotic matter shells might also explain the dark energy that currently accelerates cosmic expansion. These connections suggest that gravastars might not be isolated curiosities, but rather examples of more general principles that govern how the universe creates and maintains complex structures at its most extreme scales. If we can identify these underlying principles, we might discover that exotic objects are far more common than we currently imagine, representing natural solutions to problems posed by the fundamental architecture of spacetime itself. The philosophical implications of these discoveries extend far beyond physics into questions about the nature of existence and our place within the cosmic order. If the universe routinely creates objects whose internal structure defies our everyday understanding of matter and energy, what does this reveal about the relationship between the possible and the actual? Are we living in a cosmos where mathematical consistency is the only constraint on what can exist? These questions challenge our most basic assumptions about the relationship between theoretical physics and observable reality. How do we develop confidence in predictions about phenomena so extreme they might never be directly testable? What constitutes evidence in realms where controlled experimentation is impossible, and where the relevant processes unfold over timescales that dwarf human civilization? The search for answers has led physicists to develop increasingly sophisticated techniques for extracting meaning from limited observational data. Machine learning algorithms trained on theoretical predictions are learning to recognize patterns that human analysts might never notice. Searching through vast databases of cosmic observations for subtle signatures that could reveal the presence of exotic physics hiding in plain sight. These artificial intelligence systems represent a new kind of cosmic archaeology, capable of sifting through decades of accumulated data to find correlations and anomalies that could point toward revolutionary discoveries. They're teaching us that the universe might already be showing us evidence of exotic phenomena, hidden in observations we collected before we knew what to look for. The interdisciplinary nature of Gravastar research continues to break down traditional boundaries between different areas of physics. Techniques developed for studying quantum phase transitions in condensed matter systems find unexpected applications in understanding how exotic matter might behave under gravitational stress. Methods from particle physics provide insights into the quantum field configurations that could stabilize these remarkable objects. This convergence of different theoretical approaches is revealing new perspectives on fundamental questions that have puzzled physicists for decades. The problem of unifying quantum mechanics and general relativity, that central challenge of theoretical physics, might find its resolution not in abstract mathematical frameworks, but in the concrete study of objects that exist at the intersection of both theories. The mathematical tools required to explore these possibilities continue to evolve at a remarkable pace. Each new theoretical development opens doorways to phenomena we never anticipated, revealing that the equations of general relativity contain far more information about possible realities than their creators ever imagined. The mathematics itself seems to be teaching us about aspects of the universe that we're only beginning to recognize. Working at these frontiers requires a unique blend of mathematical sophistication and physical intuition that pushes researchers to their intellectual limits. The solutions that describe exotic compact objects exist in narrow parameter ranges where every assumption must be carefully justified and every calculation meticulously checked. It's like exploring a vast mathematical landscape where each step forward reveals new territories that demand their own specialized techniques and conceptual frameworks. The energy scales involved in Gravastar physics create environments so extreme they serve as natural laboratories for testing our most fundamental theories about the nature of matter and spacetime. The forces that maintain exotic matter, shell stability, operate with intensities that exceed anything we can recreate in terrestrial experiments by factors that render comparison meaningless. Yet these enormous energies exist in states of perfect equilibrium, balanced through quantum processes that operate according to principles we're still learning to understand. This equilibrium represents a triumph of mathematical elegance over physical intuition. Classical physics would consider such configurations impossible, yet the equations of quantum field theory in curved spacetime not only permit them, but suggest they might be inevitable consequences of sufficiently extreme gravitational conditions. It's a reminder that the universe operates according to mathematical principles that often transcend our everyday understanding of how things should behave. The temporal aspects of Gravastar physics create additional layers of mystery that challenge our conception of how complex systems can maintain themselves over cosmic periods. From our external perspective, these objects might preserve their exotic structure for longer than the current age of the universe. Yet, from the perspective of observers within the exotic matter shell, where time flows according to different rhythms due to extreme gravitational effects, the maintenance processes might unfold according to entirely different chronologies. This relativity of temporal experience creates paradoxes that force us to reconsider our most basic assumptions about the nature of time itself. If different regions of a single object can experience time at dramatically different rates, what does this mean for concepts like simultaneity and causality? that form the foundation of our understanding of physical processes. The study of these temporal effects has implications that ripple outward through every aspect of theoretical physics. Our models of cosmic evolution, stellar formation, and galactic dynamics all assume a universal time coordinate that might break down completely in the vicinity of exotic objects like Gravastars. We might need to develop entirely new frameworks for thinking about how the universe unfolds when time itself becomes a dynamic variable shaped by quantum processes. The observational signatures of these temporal distortions would be extraordinarily subtle, detectable only through the accumulated effects of many interactions observed over extended periods. Yet these signatures might already be present in data we've collected, waiting for theoretical frameworks sophisticated enough to recognize their significance. The universe might be constantly showing us evidence of exotic physics, hidden in observations we haven't yet learned to properly interpret. As our understanding of Gravastar physics continues to evolve, we find ourselves repeatedly confronted by the inadequacy of our existing vocabulary to describe what we're discovering. Terms like matter, energy, space, and time, which serve us well in familiar contexts, begin to lose their precision when applied to objects that exist at the intersection of quantum mechanics and general relativity. We need new language to match the new realities we're uncovering. This linguistic challenge reflects deeper issues about the relationship between mathematical description and physical understanding. The equations that govern Gravastar behavior often lead us to conclusions that seem to contradict common sense, yet they emerge naturally from well-established theoretical principles. We're being forced to expand our conception of what's possible in ways that challenge the very foundations of how we think about reality. The future of this field lies not just in better observations or more sophisticated calculations, but in developing entirely new ways of thinking about the relationship between theoretical possibility and physical existence. We're learning that the universe might be far more mathematically rich than we ever imagined, containing solutions to physical problems that transcend the categories we use to organize our understanding. In the gentle darkness that surrounds us, where light itself becomes subject to gravitational forces so intense they reshape the very meaning of illumination, these exotic possibilities wait patiently for discovery. They exist in that beautiful realm between the known and unknown, where human curiosity encounters the fundamental mysteries of existence in their most extreme manifestations. As we continue our journey through these cosmic enigmas, we find ourselves humbled by the recognition that we're only beginning to explore the true depths of what the universe contains. The mathematical beauty that emerges from Gravastar theory serves as a constant reminder that reality operates according to principles far more elegant and surprising than our everyday experience would suggest. In the delicate balance between quantum pressure and gravitational collapse, in the hollow cores filled with negative energy density, in the shells of exotic matter that exist in states unknown to terrestrial physics, we glimpse reflections of truths about the cosmos that we're only beginning to understand. These objects, whether they exist as mathematical curiosities or as actual inhabitants of the cosmic zoo, continue to expand our sense of what's possible in a universe that refuses to be constrained by our limited imagination. The implications of Gravastar research extend beyond the realm of pure theory into territories that challenge our deepest assumptions about the nature of scientific discovery itself. we find ourselves in the peculiar position of studying objects that might exist at the very boundaries of what can be known, where the distinction between mathematical possibility and physical reality becomes beautifully blurred. Consider the extraordinary journey that has brought us to this moment of cosmic contemplation. A century ago, the idea that space and time could be warped by matter seemed like pure fantasy. The notion that massive objects could bend light itself defied every intuition humans had developed about the nature of reality. Yet Einstein's equations insisted these phenomena must exist, and eventually, observations confirmed what mathematics had predicted decades earlier. Now we find ourselves in a similar position with Gravastars, standing at the threshold of discoveries that could fundamentally alter our understanding of what's possible in the cosmic arena. The mathematics tells us these objects could exist, emerging from the same theoretical framework that has successfully described black holes, neutron stars, and the expansion of the universe itself. Yet their properties are so exotic, so far removed from anything in our everyday experience, that accepting their possibility requires a leap of imagination comparable to those made by the pioneers of relativity theory. The observational challenges we face in searching for these cosmic enigmas reflect deeper truths about the nature of knowledge at the extremes of physical possibility. We're attempting to distinguish between objects that appear nearly identical from our distant vantage point, looking for signatures so subtle they exist at the very threshold of what our instruments can detect. It's like trying to read a book written in a language we're still learning, where every sentence could contain clues about the fundamental structure of reality. The gravitational wave astronomy that has revolutionized our understanding of compact objects operates according to principles that would have seemed magical to previous generations of scientists. We're literally listening to the sounds of space-time itself, detecting vibrations in the fabric of reality that carry information about events occurring billions of light years away. Each detection represents a kind of cosmic archaeology, revealing secrets about the universe's most extreme environments. The data streams flowing from these extraordinary instruments contain patterns so complex that human analysts working alone could never hope to decode them completely. Machine learning algorithms have become essential partners in this quest. They're artificial neural networks trained to recognize signatures that might distinguish exotic objects from their more conventional cousins. These digital assistants are teaching us to see patterns we never knew existed, hidden in the cosmic symphony of gravitational waves. The theoretical frameworks we use to interpret these observations continue to evolve with breathtaking rapidity. Each new insight opens doorways to possibilities we hadn't previously considered, revealing that the mathematical landscape of general relativity contains far more richness than we initially realized. The equations themselves seem to harbor secrets about the nature of reality that we're only beginning to discover. Working at these frontiers requires a unique form of intellectual courage, a willingness to follow mathematical logic into territories where physical intuition provides little guidance. The researchers exploring Gravastar physics must navigate parameter spaces so complex that small changes in assumptions can lead to dramatically different predictions about observable phenomena. It's like exploring a vast theoretical wilderness where every path forward reveals new territories that demand their own specialized tools and techniques. The computational challenges posed by these exotic objects push our technological capabilities to their absolute limits. Simulating the behavior of quantum fields under extreme gravitational conditions requires solving equations so intricate that even our most powerful supercomputers can only approximate their solutions. Yet within these computational struggles lie hints of deeper patterns, suggestions that the universe might operate according to organizing principles we're only beginning to recognize. The philosophical implications of this research extend far beyond the specific question of whether gravastars actually exist. We're exploring fundamental issues about the relationship between mathematical consistency and physical reality, about the role of observation in determining what we consider to be true. If the universe can create objects whose internal structure transcends our current understanding of matter and energy, what does this reveal about the nature of existence itself? These questions touch on ancient mysteries that have puzzled humanity since we first began to wonder about our place in the cosmic order. The relationship between the possible and the actual, between what can be imagined and what can be real, becomes particularly acute when we're studying phenomena that exist at the very limits of observability. We're forced to develop new frameworks for thinking about evidence and explanation in contexts where traditional experimental methods simply don't apply. The search for Gravastar signatures has led to unexpected connections between seemingly unrelated areas of physics. Techniques developed for studying phase transitions in condensed matter systems find applications in understanding how exotic matter might behave under gravitational stress. Methods from particle physics provide insights into quantum field configurations that could stabilize these remarkable objects. The boundaries between different research areas are dissolving as we recognize that extreme physics requires a synthesis of all our theoretical tools. This interdisciplinary convergence is revealing new perspectives on problems that have puzzled physicists for generations. The quest to unify quantum mechanics and general relativity, that central challenge of theoretical physics, might find its resolution not in abstract mathematical frameworks, but in the concrete study of objects that naturally exist at the intersection of both theories. Gravastars could be nature's own laboratories for quantum gravity, places where the deepest questions about spacetime find their answers. The energy scales involved in these phenomena create environments so extreme they serve as natural testing grounds for our most fundamental theories. The forces that would maintain gravastar stability operate with intensities that dwarf anything we can recreate in terrestrial laboratories, yet they must be balanced with mathematical precision that admits no margin for error. It's a reminder that the universe routinely creates conditions far more extreme than anything we can artificially produce. The temporal aspects of gravastar physics introduce additional layers of complexity that challenge our understanding of how time itself behaves under extreme conditions. These objects might maintain their exotic structure for periods longer than the current age of the universe, yet they remain fundamentally dynamic systems where quantum processes unfold according to rhythms that have no parallel in our everyday experience. This creates paradoxes about the nature of stability and permanence that force us to reconsider some of our most basic assumptions about how complex systems maintain themselves over cosmic periods. The quantum mechanisms that would preserve gravastar structure operate according to principles that blend deterministic equations with probabilistic outcomes in ways that stretch our understanding of how causality propagates through curved space-time. As we reach the end of our cosmic journey tonight, we find ourselves changed by the profound mysteries we've encountered together. Gravastars represent more than exotic theoretical objects. They embody the universe's endless capacity to surprise us, to reveal possibilities hiding within the elegant mathematics that governs reality itself. Whether these hollow giants exist in the cosmic darkness or remain beautiful mathematical dreams, they remind us that we've barely begun to explore the true depths of what's possible. Sweet dreams, fellow cosmic wanderer. The universe keeps its secrets well, but our curiosity burns eternal.